Hello, my name is Adria HUGUET-FERRAN and I am a Ph.D. candidate at the University of Barcelona and the CTO at Kumux, a spin-off of the same university. In this presentation I will talk about spectral engineering and this project I have been working for the last 6 years. We were born at the Faculty of Physics and now we are at the Barcelona Science Park, both situated in the Barcelona Knowledge Campus. The presentation is divided by 3 different blocks. The first one is spectral engineering topics, the second one is a case scenario applied to the showroom we have installed at the Science Park, and finally we'll talk about the software usage and possibilities. Let's remember what engineering is. Engineering is the activity of applying scientific knowledge to the design, building and control of machines, roads, bridges, electrical equipment, etc. And if we apply this definition to light, these 2 questions arise. Why do we need spectral engineering? And do we have the right tools to analyze, create and manage new advanced LED fixtures? Or in other words, is there any software in the market to help us to design new light recipes with all visual and non-visual parameters? Answering to the first question, we need spectral engineering to apply the scientific knowledge in so many different scopes, including these 3 popular applications: colorimetry, human-centric lighting and horticulture. Spectral engineering has an important role in creating state-of-the-art devices and environments so that they comply with the most demanding benefits, such as creating a fixture with a super high color rendering index, a room with a very low melanopic flux, or a greenhouse designed for an optimal tomato growth. We have been visiting several lighting companies and most of them are using Excel files for creating new light recipes for their multi-channel fixtures. Using an Excel file and setting the different colorimetric and non-visual parameters manually is like use a printed map to define a route in a road trip. Nowadays we have applications that optimize the path between 2 cities, and they give us the perfect option out of thousands of possible options available in just a second. Finding a perfect solution is very hard, since all the parameters change at the same time while moving a value of one channel. I know that this Excel file on the left is not the most advanced of the Excel files, but I think that is easy to get the point. To show the complexity of spectral engineering, I will use MP ratio as example. We all know what photopic vision is. It's the vision in daylight conditions that involve the cones of the retina. Also, we can define the melanopic vision as the vision related to the human body's neuroendocrine response carried out by the intrinsically photosensitive retinal ganglion cells. The melanopic vision is connected to the circadian response in humans, and the melanopic spectral efficiency function has a peak around 490 nanometers, situated on the blue region of the visible range. So if we divide the melanopic vision by the photopic vision, we get the melanopic photopic ratio, also known as MP ratio. I have chosen the MP ratio because it is often wrongly related to the CCT, although we will see this relationship between them, and because it has a direct relation to the equivalent melanopic lux, EML, which is broadly used, for example, in the WELL certificate. To get the equivalent melanopic lux, you just have to multiply the classical illuminance in lux by the MP ratio. To see the relationship between the MP ratio and the CCT, at Kumux we have analyzed over 1,000 LEDs, and here we can see the white ones in the CIE 1931 colorimetric diagram and the position of every LED on the MP ratio versus CCT chart. If there was a relationship between these 2 parameters, this point cloud would be a straight line. However, it is very easy to find out that there are a lot of LEDs with similar MP ratios but a very different CCT and vice versa. Let's go deeply and talk about particular cases. For example, in this slide we have 2 different commercial LEDs with a difference of CCT of 1500 kelvins but with no MP ratio variation. Remember that the maximum of the melanopic spectral efficiency is situated at 490 nanometers, so the amount of radiation around this value is crucial when calculating this parameter. Another interesting example could be this one, 2 LEDs with practically identical CCTs but with a huge variation of the MP ratio. And what happens if we add the CRI as a new variable in this chart? We can say that when comparing phosphor-converted white LEDs and variations of this technology, the relationship between these 3 parameters seems more clear. For example, we can say that a commercial white LED of 4000 kelvins 80 CRI has an MP ratio of more or less 0.65. However, as discussed later, this relationship is not generally applicable. Nowadays in the market we can find a lot of different fixtures with more than 2 channels. Here I present you a system we have installed on the showroom in the Barcelona Science Park, that it is composed by 5 different LEDs: red, green, blue, warm white, and cool white. We can create different light scenes, taking into account a lot of different colorimetric, non-visual, and power parameters. One of the most interesting possibilities of the system is the production of metamers. Many spectra can appear the same, but it can have very different light properties. The metamerism is the perceived matching of colors with different non-matching spectral power distributions. Colors that match this way are called metamers. If two light sources with different spectra are directly observed, it is possible to perceive the exact same color if they are metamers. However, they can deliver different light properties, such as CRI or MP ratio, and of course, they can have different energy efficiency. Here we have a video example of two metamers. The first one is a cool white LED working alone with no other contribution. The second one is a mixture of light composed by the 5 LEDs of the fixture. The color is perceived as the same since there is practically no variation in the colorimetric diagram, but the difference in the CRI is clearly appreciable. If we take a look on the capabilities of the system when comparing to the commercial white LEDs, we can see that it is possible to achieve very high MP ratio values. We can have CRI 80 combinations with MP ratio above 1 in CCTs greater than 4000 kelvins. Moreover, if we look at the chart on the right, we can see that it is possible to achieve CRI 95 values from 2400 kelvins to beyond 7000 kelvins. The white LEDs working alone have both CRI 84, and their election was related to the high energy efficiency they have. However, if we select LEDs taking into account the MP ratio, we can have a system that can achieve practically any MP ratio available on the market. At 4000 kelvins, for example, we can have a CRI 80 combinations with an MP ratio that can go from 0.4 to 0.8. If we look at the CRI versus CCT chart, we can have values of CRI 95 from 2000 kelvins to 7000 kelvins and beyond. This means that we have the technology to achieve practically any value available on the market, and this technology on a multi-channel system depends more on the global selection of LEDs than the individual selection of white LEDs of the fixture we're creating. Furthermore, the relationship between CCT, MP ratio and CRI is not applicable in multi-channel systems. This is because these systems can deliver a lot of different spectral shapes, as opposed to commercial white LEDs that generally have similar shapes. So, using a multi-channel system enables us having full control over the light properties and going beyond the possibilities offered by the market. However, shaping the spectrum that matches our interest can be really hard, because all the light parameters are interconnected. If we increase, for example, the intensity of the red channel, it will have consequences on the decreasing of the CCT and MP ratio, but also varying the CRI, R9, energy efficiency, distance to the Planckian locus, etc. We can use a multi-channel system for different purposes, so the same fixture can be reused in multiple projects. However, we need tools to create and manage new light recipes, because the use of Excel files and derivatives represent a bottleneck for the development of this technology. Kumux is the answer for lighting companies and lighting designers who are willing to find the right spectrum for their needs, simulate and develop new products, reducing your cost up to 70%. The process follows the flow shown in this figure. You will be able to create a LED PCB, run the simulation algorithm, and select the spectra that fits your interests. Then the results can be exported and embedded into any control system and reproduce the simulated spectra. In this video, we can see the creation process of a LED's PCB. Simply drag and drop the LEDs and set the number of LEDs in series, parallel, and the driver current for each channel. You can select any of the 1000 LEDs of the database, which is the same database I presented before, plus the color LEDs. The information of each LED can be seen in a standardized format, and you can search the LED you want using the filters. As the information on the PCB is updated, the spectral power distribution chart corresponding to the maximum intensity of the different channels is also updated. Another interesting point is the possibility of adding your own LEDs. The process is also easy to follow, as you can see in this video. Adding your custom LEDs is a necessary step in order to reduce at the minimum the error between the theoretical data and the reality. This error has three different components: binding, thermal variation, and the effect of the diffuser in the fixture. All the lighting manufacturers know these three problems that affect the final shape of the spectrum. If we make the calculations with these errors corrected, the results of the simulation will match perfectly with the reality. Once the LED PCB is created, we can start the simulation process in order to find all the possibilities of the fixture we are creating. The problem to solve is similar to find a needle in a haystack, because it is possible to generate billions and billions of combinations by mixing the light of the LEDs at different intensities. The question is, which combinations are the most suitable? We have developed our own intelligent algorithms in collaboration with the Barcelona Supercomputing Center. Out of the billions of possible combinations, the software result is composed by the most relevant ones, helping you to find the right combination in a matter of seconds. Let's create together a recipe. It will be a scene with a high MP ratio, but also with a very short distance to the Planckian locus and a minimum CRI value of 80. The only thing we have to do is to change the values in these sliders, moving the limit parts or setting the values manually. Another option is to set the toggles, and all the other parameters and charts will update automatically. We can observe the CIE 1931 diagram is showing all the time the combinations left and their situation. Once there is only one combination left, we will be able to save the scene and review its characteristics. An automatic report will be generated, and we will have access to other charts such as the CRI values, the color vector graphic, or the fidelity saturation chart of the TM3018 standard. The second scene we can create is a low CCT but with very high CRI. We are using a warm white LED that has a moderate CRI value of 84. Using the software, we can create a recipe that has the same CCT of the warm white LED of the fixture but with a CRI of 95. We follow the same procedure as before and save the scene we just rapidly created. All the scenes can be exported to a file that includes the electrical current values of the different channels of the fixture we have created. Then, we can reproduce these scenes in the reality and check that everything matches. So here we have the lessons learned to summarize. We have talked about the spectral engineering, the MP ratio and its relationship with the CCT and CRI in white LEDs, the Metamers and multi-channel systems, and finally Kumux and its benefits and procedures. Well, thank you very much for your attention, and if you have any question you can contact me through email or LinkedIn. Stay safe!